Ready to start? Today we want to finish up on polar coordinates and the calculus thereof. So we're going to do arc length. We did area last time in polar coordinates. This time, arc length. All right. And we'll do a few polar figures along the way too. Kind of interesting things come up. So let me see if I get this straightened out just a little bit here. There we go. Recall from what we did with parametric curves that the arc length of a curve given parametrically by the points x of t, y of t. Parametrically just means x and y are both functions of another variable called a parameter t. So t runs between two numbers a and b, let's say. What was the arc length formula, remember? Hopefully. It was the integral from a to b of the square root of dx dt squared plus dy dt squared. We had to derive that one by taking the limit of the sum of the line segments, maybe you recall. Now we can apply that to polar coordinates for curves given in this form. We'll assume that this thing is smooth. By that we mean it has a continuous derivative. So there's no corners in it or anything. R given as some function, let's call it r of theta, right? It's like we called it r of theta or f of theta when we did the area problem. Suppose again r is given as a function of theta. How can we apply this curve or this arc length formula? Well, we know that x is equal to r cosine theta, and along the curve, x is r of theta cosine theta, right? As we move along the curve. And similarly, y is equal to r of theta sine of theta as you move along the curve, right? If I call this equation here star, the old arc length formula, all of a sudden you realize this curve is x and y given as a function of theta instead of t, right? So this is a parametric curve with parameter theta. Theta going between some two numbers. Suppose this polar curve is given with theta running between alpha and beta, those angles. Then that'll be this will be a parametric curve, theta between alpha and beta. And then by star, because we have a parametric curve, the arc length is equal to, instead of a and b, we just write alpha and beta because it's angles. And what is dx dt? Well, x is this, so we have to calculate its derivative. Let me get rid of this. The derivative of x, well, it's a product, so I need a product rule. Dx dt is derivative of this gets replaced with, right, if we do theta, then the formula becomes this for a new formula. So dx d theta, we take dr d theta times cosine theta plus r times derivative of cosine theta is minus sine theta. And that's the derivative of x with respect to t by the product rule, right? Just apply the product rule to that product. Then I'll square it, and then I'll add, let's see, maybe I need one more. Oh, that's right. Thought I lost a parenthesis for a second. Now I need the derivative of y with respect to theta. Well, let's again a product, so I put dr d theta times sine, derivative of the first one times the second, plus the first one, r, times derivative of sine is cosine. And then I'm going to have to square that one. And square root of the whole thing, d theta. So there's the arc length formula applied to this kind of parametric curve, a polar parametric curve. Now I can get rid of star, I don't need it anymore. And that simplifies to a nice formula that you can compute arc length and polar coordinates. Let's see what we get. This is integral alpha to beta. And let's see. For simplicity, let's write dr d theta as r prime. So this is r prime cosine theta. And if we square this whole thing here, we've got r prime squared cosine squared theta plus 2 of these cross terms, right? This one times this one twice in the FOIL. So it's minus 2r sine theta cosine theta, r prime, if I call this r prime again, and this one too. Minus 2r r prime cosine theta sine theta. And that's this thing squared, right? The square multiplied out. Similarly, we can square this one out, right, by FOIL. And we get over here r prime squared sine squared theta. This one squared plus 2 of the cross terms, 2r r prime sine theta cosine theta. And the cross terms, and then plus r squared cosine squared. And the whole thing is under the square root and then d theta at the end. Is that okay so far? I just plug this into the arc length formula for parametric curves. I get this. And now something nice happens. This nasty term here cancels this one here. And we're left with the integral from alpha to beta of the square root of r prime squared multiplies cosine squared plus sine squared. Just factoring this. And then here we've got, well, I left off a term, didn't I? I put this, there's supposed to be a square here. This is supposed to have an r squared sine squared theta here from this one times itself, so for the FOIL. So this one plus 2 middle terms plus the last term. All right, and so then we've got an r squared sine squared plus r squared cosine squared. Looks like this, factored. And that's what's left under the square root, factoring out the r squared and the r prime squared from these terms, and then the whole thing integrated with respect to theta. Well, by trigonometry, right, we remember that sine squared plus cosine squared is 1, so we can cancel, scratch those out. They're equal to 1, multiplying these things. Now what we have is a nice formula that looks like this. Theorem. This is what we just proved. If r, given as a function of theta, has a continuous derivative on the interval alpha less than or equal to theta less than or equal to beta, the arc length, let's say its arc length, is this formula we got right here at the bottom. It's the integral from alpha to beta of the square root of r prime squared, which I can now write as dr d theta squared if you want, plus r squared d theta. There it is. We call that equation double star, huh? Now we can find nice arc lengths in polar coordinates, just like we could find arc lengths in rectangular coordinates, right? We got a fairly straightforward formula. So that one's to memorize. I usually put a star by those to memorize. And we could do a simple problem like this. Find the arc length of this polar curve, r equals 6 theta squared, where theta runs from 0 to 2 radians. All these things are assumed to be in radians. Why do we always in calculus take radians? You ever thought about that? Maybe I mentioned at the beginning of the course. It's because all the formulas are easier, right? If you take, for instance, the derivative of the sine function, y equals sine x, where x is in radians, then the derivative y prime is the cosine function, right? It's easy. But if this was in degrees, what would you have to put? Rewrite it for the degrees function. Sine in degrees is, you have to write this by pi over 180x. That's the degree sine function. And now the derivative is cosine x times pi over 180. And so every time you take a derivative, you get this extra conversion factor to convert. And same thing with integration, you get a conversion factor. And so everywhere you go, you're having to change things over. Radians is so much more useful for calculus. And we do that in these arc length formulas here too. So we'll assume theta is in arc length in radians when we use these formulas. Otherwise, we'll have to put in a conversion factor. All right. Suppose we want to do that one. What's the arc length of that curve? Using formula double star. Well, it's pretty easy. We just calculate dr d theta. All right. Derivative of 6 theta squared is 12 theta. So the arc length by this formula then is the integral, theta going from 0 to 2 in this case, square root of 12 theta squared plus r squared. R is 6 theta squared. So I get 6 theta squared d theta. This might look kind of like an integral you've seen before. And while in general this integral has the drawback that with the square root makes it seldom you can actually evaluate the integral, in this case we can. The problems will tend to have ones you can evaluate, right? So we'll say this is the integral from 0 to 2, square root of 144 theta squared plus 36 theta to the 4th d theta is integral from 0 to 2. And if I factor out a theta squared out of here and pull it outside the square root of theta, and also a 6, I could put a 6 theta outside just by algebra, and have 4 plus theta squared on the inside. Yeah. So right, 6 theta brought in is 36 theta squared times this one, it gives 36 theta to the 4th. 36 theta squared brought in here times 4 gives 144 theta squared. Now what do we see? U substitution, right? You can let U be this one. Then du will be just a multiple of what's outside. Du is going to be 2 theta d theta, right? Derivative of this times d theta, which says by division that 1/2 du can replace theta d theta that we have in there. So I'll just take the theta d theta substitution, right? Scratch out and put 1/2 du. I'll take out 4 plus theta squared, scratch it out, and put u. And now the integral becomes 6 times 1/2 du. Well, let's say 6 square root u, 1/2 du. Right? Theta went from 0 to 2. When theta equals 0, u is 0 squared plus 4 is 4, so I have to start at 4. When theta was 2, we've got 2 squared is 4 plus 4 is 8. So now we're going to go from 4 to 8 in u. And this will wind up being, well, let's see, half of 6 is 3. I can write that as 3 integral from 4 to 8 of u to the 1/2 du. And I know how to integrate that, right? This is 2/3 u to the 3/2. Plug in 4 and 8 and take the difference. The 3's cancel. And I've got twice 8 to the 3/2 is 8 square root of 8. It's 16 square root 2, I guess. And then 4 to the 3/2 is 8. Simplifies a little. I guess that writes as 16 times 2 square root 2 minus 1. But there's the exact arc length for that curve given in polar coordinates then. This is a spiral if you think about it, right? The equation was r equals 6 theta squared. Get a better pen here. R increases as the square of theta, so how do you sketch it? You can make a few. Actually, can I erase this? Are we far enough along that I can erase some of that? I just thought it was worth graphing. One of the things you want to get out of this section also, even though it's not real explicit about that, is you want to be able to graph these. What does this look like? R equals 6 theta squared. Typically, the way you do these when you write r as a function of theta is you plot r versus theta, and you put in values of theta and then plot r. So I put theta equals, the first value in there was 0, as I recall, 0. And so r 6 times 0 squared is also 0. So you start at the pole, right, r equals 0. Then you make theta a little bigger. Maybe you make theta equal 1/2 or something. When theta equals 1/2, you got 6 times 1/2 squared is 6/4 or 3/2, right? So you put in theta and r, and then to plot it, what you do is you turn to this angle and move out this far. Well, what is 1/2? This is 0.5 radians. 1 radian, if you remember, is equal to, well, it's 180 degrees per pi radians. It says it's about 180 over pi is about 60 degrees. It's a little less. I think it's about 57, if I recall. So what I've done is that when I've turned to about a 60-degree angle, not quite to 60, I'm supposed to have gone out 3/2 units. So if this is 1, 2, then I measure out this way, 1, 2, and it's about right there. So as what's happening is as theta is turning, r is getting bigger. So I've got a curve that's moving like that. Now I plot theta equals 1 maybe. That's about almost 120 degrees, probably 115 or so. Then I get 6 times 1 squared is 6. So when I turn out over this way to about 120 degrees, and that's what you can do. Here's theta equals 1 radian. Here's theta equals 2 radians. You turn to the angle and move out that far. Turn to the angle. Now I got to move out 6 units. That's about as far as I can draw. So this would be the point r equals theta. R equals 6. Theta equals 1. This would be the point here. R equals 3/2. Theta equals 1/2. And you can, so 1, 2, 3, 4, 5, 6, like that. And the curve then that you're plotting is a big spiral that goes out rather quickly like that, right? But because it starts at angle 0, as long as it's a smooth function, the initial tangent vector will be tangent to the curve like this. So it starts out tangent to the x-axis and turns like that, is what it does. A famous one of these is r equals a number a times theta. Here we did a times theta squared. This goes out rather quickly. R equals just a constant times theta. Apparently I need another pen again, huh? A constant times theta is called an Archimedean spiral, after Archimedes. But when you see R increasing with theta, then you can think, oh, it's spiraling around. Is one hint in drawing these things, right? And what we did was we went from, I guess, to 2 radians, so we went a little further. We went all the way out to twice this, about here somewhere, and we found the arc length of this thing. So these are like a coil of rope has an Archimedean spiral like that. There's also logarithmic spirals that are really useful. R equals a e to the b theta is a logarithmic spiral. These things you find like in nautilus shells and so forth. They spiral out rather quickly like that. As the nautilus grows, it makes a bigger and bigger shell as it goes out. Galaxies, I think, are somewhat logarithmically spiral shape, if I remember spiral galaxies. There may be some of those pictures in your book. I didn't check, but a lot of textbooks will have spirals like that to show you. But this would be like a coil of rope, equally spaced, and an Archimedean spiral. This one's faster, and this one's exponential, goes out real fast. All right. So that's that part. Now, along with this comes some fun curves. The book does not spend a whole lot of time on these, but you want to be introduced to them a little bit because they're in moderately common usage, not terrifically common usage. Other other curves in polar coordinates that are convenient in polar coordinates, that is, include the following. Suppose I had R equals A times cosine theta. I don't think the book does a whole lot to point this out. It does use it, but what would that look like? If you tried to plot it again, and this is one thing I want you to pick up. Suppose you put theta, you could do R and theta again and sort of figure out what it looks like. But what's easier in this one is to convert coordinates. We did some of these before, right? If I take this one and multiply it through by R, we say we could rewrite this as R squared equals AR cosine theta. In fact, let's write it this way, 2A cosine theta. I'll put a 2 in here. It's convenient. This then becomes x squared plus y squared equals 2ax, right? If I multiply through by r, then this is easier to convert. R cosine theta is x. R squared is just x squared plus y squared without a square root, which was right better than this. Now, if I transfer this over and complete the square like we showed in the other examples last time, we have this. And what do I do with that to sketch it, maybe? Yeah, you could solve for y. I'm going to do something else, though. That is a good idea, actually. I'm going to add a squared in traditional what we did last time. I'm going to add a squared to each side. Because that's going to make this a square. Now I can write this as x minus a squared plus y squared equals a squared, which is what? Recognize that equation? Oh, come on. X minus x0 squared plus y minus y0 squared equals r squared is a circle of radius r, right? Yeah. So this is a circle at A0 of radius A. It looks like this. It just kisses the origin there. A0, and then it goes out to 2A like that. So this is a useful curve in polar coordinates. R equals a number times cosine theta, or R equals a number times sine theta. You can complete the square and sketch the circle. All right? So R equals 2A sine theta. Similarly, is a circle of radius A going up the y-axis. And if you put a negative A, you can make it go down or left. So this is a circle at 0A going up to 2A. And these turn out to be a special case of something else that I don't really see in this section, but I'll just mention it in passing. They do have these circles, but these are special cases of things that are commonly plotted in polar coordinates, and I think are elsewhere in the textbook. Roses. Polar plots of what are called roses. R equals A, let's just put A instead of 2A this time, cosine n theta, and R equals a sine n theta. And you let A be positive or negative as you like. And n is supposed to be, right, an integer, but A is a real number. So you get what you get out of this is when n equals 1, you get a circle, right, from what we just said. N equals 1, you get this circle that we call a one-petal rose. All right. But if you keep plotting, it does something interesting. Let's do an R versus theta chart here. If I put in, for instance, this one, R equals, let's just choose A equals 1, sine of 3 theta, right? What does that look like? What could that look like? What you can do is start at theta equals 0, and then sine of 0 is 0, so R is 0, and you think about your special angles. To get a special angle here, I could next put theta equals pi over 9. That'd be one way. Then I'd get pi over 3 in here, and sine of pi over 3, if you recall, is square root 3 over 2. If I were to put pi over 6 in for theta, I'd get a sine of a special angle pi over 2, which would be 1. And I can keep going. If I put, let's say, 2 pi over 9, then I can take the sine of 2 pi over 3, which is again square root 3 over 2. And if I put in pi over 3, sine of 3 times pi over 3 sine of pi is 0 again. And so what I've done actually by going through these special angles is I've figured out some points on some sort of curve that starts with r equals 0 and finishes r equals 0, going to a maximum distance from the origin, r equals 1. It is one petal of this rose. And it looks like this. Here's how you sketch these kind of things. You start with theta equals 0 going in this direction, and you're at 0, so you sketch the pole. Then when theta turns to pi over 9, a very small angle, right? It's Pi over 3 is here, and you're 1/3 of that, so you're down here. Theta equals pi over 9. You're supposed to go out square root 3 over 2 units. So maybe this is 1, 2. So square root of 3 is about 1.7. So you're about here, right? You can mark off 1, 2 on there. And the idea is you start out at this angle, tangent to the x-axis, and go around to this point. Now at pi over 6, you get out to 1 unit. That's your maximum distance. This is 30 degrees, pi over 6, right? Now I'm out. Oops. I'm sorry. Square root 3 over 2 is half of 1.7. I guess this would be 1 here. So it's 0.7. Sorry about that. And then you get out to 1 unit out when you're up here. There's 1 unit. And then it comes back the same way at 2 pi over 9, like that. You're back to this distance, square root 3 over 2. And then when you get over to pi over 3, this angle here, you come back to the origin just tangent to that angle. And there's 1 petal of a rose. If you keep going on this, what you'll find, ... Since the book doesn't have problems on it, this section, I don't want to get into a lot of this, is that it goes back around like this, makes another petal down here the same length, and another petal here the same length. This one actually has R negative. You're taking through these angles, you'll take this angle and then plot R negative down to here. This angle here, if you put in, for instance, pi over 2, you'll take the sine of 3 pi over 2, which the sine of 3 pi over 2 is -1. And so at this angle, pi over 2, you go -1, you go down to right here. So that's the point you get when you put in pi over 2 for put it backwards. Pi over 2 for theta, and you get -1 for r. And it sweeps out this one with r negative, then it does this one again with r positive, and it sweeps out a 3-petal rose when you put n equals 3 in here. It turns out more generally something interesting happens, and I don't think it's pointed out in this section, but maybe later. These are roses, and what you get in both cases, all this does is change the orientation. If you put cosine, then the petal starts out along the x-axis instead of over here. But you get n petals if n is odd. And it turns out if you just keep going all the way from 0 to 2 pi, so it starts repeating, that you get 2 n petals when n is even. I think this helps you, even though they don't really introduce it so much in this section. It helps you to figure out what's going on in some of these problems you're asked about later. So those are roses. That's another thing. Spirals is one kind of polar curve that's popular. Roses is another. And they have these kind of equations. Right? Recognize when n equals 1, you get circles, and when you get higher n, you get these multi-petal roses. That helps you. But this technique of just turning to theta and going out, turning to another theta and going out, turning to theta, and really helps to have a feeling for how to sketch in polar coordinates too. Any questions on that one? I'm just going to do one more kind of polar curve. There's one in your homework on lemniscates, which is kind of a figure-8 shape that's popular in polar coordinates. I'll just let you see that in the homework, and come see me online if you have questions about it. It's just an example of finding arc length, I think. A limison is another popular curve in polar coordinates. It's a curve r equals a plus b cosine theta. R equals a plus b sine theta. These kind of things. And a or b can be positive or negative too. Sometimes they put plus or minus to emphasize that. These have different shapes if you plot them that same way. Turn through theta and go out r, turn through theta and go out r. These have interesting shapes like this. Tempted to do one, but I think let's not do it yet. You can get, as a special case, well, let's start this. You can get a figure that looks like this, kind of oblong, and the cosine turns this direction. The sine would be turn 90 degrees from there. That's a limison. If you make with A a lot bigger than B, so A much bigger than B, if A is not so much bigger, I think this A has to be at least twice B or something like that. You can get a limison with a dimple that looks kind of like that. A between 1 and 2B, I think it is. If you put, let's, so this is A, I think, greater than or equal to 2B. But in this case, you get a dimple. This one you can call a convex limison because it doesn't dimple. Then if you make A equal B, or and absolute, you can also have absolute negative numbers there, so you should put absolute value on these in case you want to use negatives. Then if you have absolute value of A equal absolute value of B, then when cosine is -1 and A equals B, you can get R equals 0. You can touch the origin, and this dimple collapses in here, and it becomes a heart shape. So this one pointing this way, for instance, would be R equals A plus A cosine theta. A equals B. And it's a heart shape called a cardioid. Still a limison, but this special case called a cardioid. Then if you make absolute value of A greater than B in absolute value, then you can actually get R negative, right? You can, I'm sorry, less than absolute value of B. Then you can make A plus B cosine theta negative, even if A is positive, and you get this limison with a loop, so it can come through like this. So you'll see some of those pictures in the book, and it doesn't go into a lot of detail yet. Limison with a loop. Anyway, so these are limisons, and this cardioid, I think I mentioned to you before, is used in microphone theory, for instance. So they do come up once in a great while. Now we can apply our arc length and area formula, let's say, to the cardioid. That's a very popular one. This would be terrible in rectangular coordinates. You can never find the arc length formula. It's too hard, right? Writing this in rectangular coordinates is a terrible, terrible integral. But since it has a simple polar equation, it's actually tractable in polar coordinates, right? It has this easy equation. Not surprisingly, you can actually do the integral. Let's do this one. Example, find the enclosed area and the arc length of the cardioid R equals 1 plus cosine theta. Theta running from 0 to 2 pi sweeps that out once. If you do that plot, turn to the angle and go out, turn to the angle and go out. Can you plot this? Let's try plotting it. I said we should try one of these, right? If you put theta equals 0, what is R? It's 1 plus cosine 0 is 2. And if you think about it, that's the largest radius you can get, right? Because the largest cosine can be is 1, so 1 plus 1 is 2 is the largest radius you can get. Now you turn through another interesting angle. You can do all your special angles. I don't think we should take time to do all of them. But if I turn to theta equals, let's say, pi over 2, and angle pi over 2, I get 1 plus 0, and I get 1. If I turn all the way around to pi, then cosine is -1. 1 plus -1 is 0, and your radius is 0. And then if you put 3 pi over 2, again, cosine is 0, and so you get 1. And if you put 2 pi, you're back to where you started, right? 1 plus 1 is 2. And you can put in the angles in between, but I just want to say that, right, you turn to theta equals 0 and go out 2 units, so it's got this point. Turn to theta equals pi over 2, this one, and go out 1 unit, so there's a point there. But when you get back to with pi, turn to this angle, you go out 0, you get the origin. 3 pi over 2, you go out 1 unit, you get to here, and then you get back to here. And if you connect the angles, special angles in between, you get this shape that we just talked about. It is indeed a cardioid. That's what you get by letting the angles gradually sweep around here and plot, sweep around and plot, sweep around and plot. And you can do these in your calculator too, right? But that's what we're finding the arc length and area of. If we still have time, I didn't labor too long plotting it. Maybe I should do arc length first, since that's the new topic today. The arc length is the integral from 0 to 2 pi, right, over the parameter, square root of r prime squared plus r squared d theta. It's no harder than that to find an arc length in polar coordinates, right? So let's see. R prime is minus sine theta. So I've got minus sine theta squared plus r is 1 plus cosine theta. 1 plus cosine theta squared d theta. I just have to be able to evaluate that integral, and I've got the arc length. But of course, there's a trick, right? The integral is probably hard to do, but it is possible, right? We'll say that this is the integral from 0 to 2 pi of square root of sine squared theta from this one, plus, when we FOIL this, 1 plus 2 cosine theta plus cosine squared theta d theta, right? So there's the second one foiled. And now, wait a minute, sine squared plus cosine squared is 1. That and that. 1 and 1 is 2. So I've got really the integral from 0 to 2 pi, square root of 2 plus 2 cosine theta d theta. All right? Which I might simplify just a bit by writing it as square root 2 integral from 0 to 2 pi square root of 1 plus cosine theta d theta. Now, how in the world am I going to integrate that? Here's another trick that you should see. Anybody know how to do that one? Integral 1 plus cosine theta. Can you read it? It's kind of faint, isn't it? Square root 1 plus cosine theta. When have you seen something like that before? Remember this trick, cosine of 1/2 theta is plus or minus square root 1 plus cosine theta over 2, right? We can use that half angle formula in here. If we multiply that by square root 2, we get square root 2 cosine 1/2 theta is what we have in there, plus or minus square root 1 plus cosine theta. Alas, this one is sometimes negative. We have to be careful about the sign here. What we can do is say, well, this goes from 0 to 2 pi. If we instead write this as twice the integral from 0 to pi, because actually as it goes from 0 to 2 pi, it goes over the same values as when it goes from 0 to pi twice. So I'm going to go from 0 to pi and multiply it by 2. I'll get the same result as if I went from 0 to 2 pi by symmetry, right? It's going over the same values of cosine twice, but once between 0 and pi, once between 0 and 2 pi. Now I've got it because on 0 to pi, cosine of 1/2 theta is positive, or not negative anyway. So I can write this as 2 square root 2 integral from 0 to pi of square root 2 cosine 1/2 theta d theta. And I'm out of time, so let me let you go and say you can do that integral pretty easily, right? Try the homework. I'll see you next time.